Hello, it's Keith here, and this is lesson 2 of the Photon tutorials, in which we look at my little Tron clone game, and we're going to go through some of the code and learn how it works. Today we're going to be having some fun because we're going to be looking at the line drawing routines. Now, Photon uses a preset routine, which is platform specific on each system, which draw a pixel to the screen in whatever way is possible, or required rather, on those systems. The line drawing routines use that preset and extend it to draw a line, and the vector drawing routines will draw an entire graphic like the title screen that you can see here, and this works on a wide variety of systems. For example, here's the ZX Spectrum version, and you can see we're using Spectrum colors. So we've got this nice program here that will work on all of these systems. Now, the line drawing routines we're going to be looking at today, I'm going to be honest, I wrote them myself. They're not probably the most efficient. If you want to see the most efficient line drawing routines, I think you need to take a look at Bressenham line algorithm. I think I pronounced that right. We will maybe be looking at it later because I have now got a Z80 version that I'm working on for a project that is going to be coming up quite a bit later. I've got another line drawing tutorial I'm going to be covering at some point in the future, still in the pipeline though. But the one we're looking at today, I don't think it's actually too bad. The Bressenham's line algorithm that I've written is not really much faster at the moment and possibly needs some more optimizing. But as I say, this one is okay. It's certainly enough for what we're using it for today, so I think it's worth looking at anyway. Now, the line drawing algorithm is just the start. We'll then be extending that to draw the vector graphics, and these are in Vectrex format, the packet format, and my modified Vectrex format, C packet, which uses a third less bytes. We'll see those as well today in the source code. Over we go. Okay, so we're going to be looking at this vector routine today, this vector file. This contains all of the content we'll be looking at in this lesson, and the most important thing is the draw line routine. Now, the line drawing routines work on 24-bit X and Y positions. Basically, the top 16 bits are potentially the screen coordinate, and the bottom 8 bits, the lowest 8 bits, are effectively used for half movements. Because if you think about it, if you're drawing a diagonal line, you may have 2 Y movements for every 1 X movement. The way my line drawing routine works is it's basically adding up those X movements in a low byte that is unused, and then the top 2 bytes are the actual X position. So we've got these 24-bit locations, X pos 24 and Y pos 24, and you can see we're offsetting by 1 byte because the X and Y position we're passing is basically the second and third byte. The first byte is effectively used for half pixel movements, not drawn of course, just calculated. Now, the drawline relative movement will draw from the current XY position to a new XY position, the XY position specified by HL and DE here. The draw line will specify a start position in IX and IY as well. Now, for our Vectrex routines, we need to always work in relative coordinates, but there may be cases where we want to draw an absolute line, so that's what this draw line routine is for here. Now, the draw line routine basically sets the start X and Y position and then take the end X and Y position and calculate those by subtraction as a relative movement from that start position. And that's what the draw line does, and then it just continues into the draw line relative routine here, which does the rest of the work. Now, the first thing we're doing here is we're checking we're actually being given a valid draw to do. If all of the bytes are 0 here, then we're being told to move nowhere, so we're not going to do anything. We're just going to skip over that. If they're not, though, we're going to make sure we're going to draw at least 1 dot, because otherwise this code will malfunction if it tries to draw 0 dots wide or something. So that's what we're doing there. And then what we're doing here is we're going to be using some markers. Now, if we go over to our ramdefs here, you can see the X pos and Y pos here are defined as 3 bytes wide. You can see there's a 3 byte allocation for them, but before them there is a direction marker here. Now, this is 0 or 1, and this will define if we're going left or right or up or down the screen. Basically, the movements are always positive, so if we are moving in a negative direction, we're using that marker to denote that. That's how this code actually works. So what we're doing here first is we are basically getting the X pos positioned into IX, setting that marker as 0, and then we're checking if the top bit of H is 0 or not, and if it's not 0, then effectively the movement is negative. But rather than keep HL as a negative value, we're going to flip it to a positive value, and we're going to change that marker to a 1. So we've got this function called flip HL here, and it will basically set that first byte in the definition, that's this byte here, to a 1, and then it will flip H and L to be a positive value now, so it's just negating HL there. That's what that does. So first we're doing that for the X position here in HL, and then we're doing it in DE here for the Y position. So we're doing the same thing, setting the direction marker and making sure the value in HL and DE are in fact positive. Next, what we're doing is we're going to work out which is the longer axis, X or Y here. Now what we're going to basically do is we're going to move 1 pixel in the longer axis, and then we're going to move a fraction of a pixel in the smaller axis, and the fractions are being done with that 24-bit value here. So we're basically going to set the larger axis to be a movement of 1 in 24 bits here, and the smaller axis to be a fraction. And what we're doing is we're calculating that fraction with the division function here. This function here will divide h by the value in the accumulator here, and it will return a value in HL, which will be a 16-bit result of the division of h. Basically, it's basically dividing HL by A, but it's setting L to 0, and that allows us to give a 1-byte value and divide it by the accumulator and get a fractional value in a 16-bit register pair there. Now, I should point out that this function, although it's designed to work on a 320 pixel wide screen, it can only draw a line of up to 256 pixels. That's the sort of limitation of the code here, I'm afraid. You could modify it to do more, but it was beyond what I needed for this example. So to avoid making the code more complex than required, I've kept it with that limitation. So here the y-axis is bigger, so we're moving 1 vertical pixel, and we're moving probably maybe half a pixel or something in the horizontal axis. So we're calculating the fractional horizontal move here and defining a 1 vertical pixel move for every tick. Here is the opposite. We are doing 1 horizontal move and a fractional vertical move for every tick here. So we're calculating those fractional moves here and the whole move for the direction that's moving 1 pixel per time here. Either way, we're going to end up here. Now we're using B and C as loop counters down here. We're using B as the low loop counter and C as the higher loop counter here. We're just making sure they're going to be okay here. And then we're loading the Y move into IY and the X move into IX here. And this is the main loop. So this is plotting the pixels to the screen. What we're doing here is we are getting the bytes of the X position and the Y position and the line color here. And then we are using our pset routine. Now the pset routine uses AB as the X position, C as the Y position, so it allows up to 320 pixels wide in effect for the X position, and up to 200 or up to 256 depending on how you look at it for the Y position, and the color is in D here. So that will plot a single pixel to the screen here from the top 2 bytes of the 24-bit XY position here. And then what we're doing is we are doing the 24-bit addition to the X and Y position here from the values in here. And remember, one of them will be a full pixel move and one of them will be a fractional pixel move, and that will be, of course, all have been calculated by these routines here. So this is a common routine that does it all. Now the rest of the magic is basically being done by these routines here. Now the add routine here also does subtraction, and what it's doing here is it is checking that top direction bit that we mentioned before, this bit here, and it's just seeing if that's a 1 or not. Now if that byte is a 1, then we are jumping down to this subtraction routine. Otherwise we're doing this addition, and we're doing 3 parts: the low part, which is the fractional pixel part, the high part, which is the whole pixel part, and the upper part, which is used for the 320 pixel wide screens. So these are the visible coordinates, and this is the fractional coordinate, which is needed for our partial pixel movements. And that's what's doing the work of calculating the pixel movements to draw the line. We've got an alternate version here, which honestly I don't think is actually used by this game. I took it out of the 6502 version. It doesn't seem to be needed, but it was basically just protecting all of the registers for drawing lines. I guess I used it in testing at some point. And that's the end of the line drawing routine. So it's a little bit tricky, but I don't think there's any magic super easy way of drawing a line, unfortunately, on these systems. That Bressenham line algorithm is not simpler, not in terms of code length. It might be simpler in terms of computational power, but it's not shorter in any real way, and there's lots of conditions and there's absolute value calculation and all kinds of nasty things. So it's not going to be easier on your brain, even if it's easier on the processor. Now, we use this line drawing routine to draw things called packets and C packets. Now, packets are the Vectrex format, and C packets are a slightly tweaked version which I wrote just to save a little bit of memory. Now, if we have a look here, we can see some packets and C packets. This is a C packet, and somewhere down here this is a packet. Now, a packet is 3 bytes per command. The first byte is the command byte, the second byte is a Y position, and the third byte is an X position. A command byte of 0 defines a movement, so we're moving the drawing cursor and we're not drawing a line, and there's a relative offset of the movement here. FF is drawing a line, and that will define the destination of the line, and it will draw from the current position, which is why we needed that relative line drawing routine. So that's drawing to that position, and 01 ends the drawing. So there's 3 potential commands, and most of them use an X and Y position. Y first, X second, I should point that out. Now, I got thinking and thought, well, that's 3 bytes per move, that's a bit wasteful. Can we do something about that? Well, the movements in the packet format are defining 8 bits per movement. I thought, well, hey, maybe we can save a bit. Maybe we could just use 7 bits for the movement and use those 2 remaining bits for the commands, and that's what I did. So my format uses 2 bits here and here for the command, and 7 bits for the Y position and 7 bits for the X position. And I should point out, in both the C packet and packet format, they're signed, so of course negative and positive. Really obvious if they're relative movements, I guess, but anyway. So the top bit of the Y position will be 0 in all cases except for the last command, which will be a 1. And the top bit of the X position will be a 0 for a move or 1 for a line. And apart from that, it's basically the same format. So that's what we did. Now, you can, in a crude way, create the graphics for this in the Acrosprite editor. It's not really a vector program, but there is a simple vector editor. I showed how to use it on my Vectrex tutorial, but you can create these just sort of manually if you can do the math. Anyway, so those are the 2 formats. Now we're going to have a look at the packet format first, because that's kind of the base one. So what we're doing here is we're backing up the start position of the drawing cursor. This is going to draw from the current selected position within XY pos. And so we're backing that up so that when we end, we have the position in the same as we started. And the reason for this is the title screen is built up of multiple drawers of like the smiley face and the little hands and the title and things. But the center is a consistent value. So we're backing up the starting position and we're going to restore at the end. We then read in a byte from our packet. We're passing in HL. If it's a 0, it's a move. If it's a FF, then it's a line. And if it's an 01, which we've done an inc to compare the 255, so we're now comparing to 2, then it's the last command, and we're jumping down to done, which we'll see later on. If we've got a line, we're basically loading in a byte here from HL, and we're using this sexbc command, which is Sine Extend. Don't get any crazy ideas about what that stands for. So that's Sine Extend BC, and so we're converting a 1 byte value to a 2 byte value so that we've got a valid X offset and Y offset for our line drawing command, which we're going to use just here. Now, the only thing to notice is we're actually negating the Y position here, and that's because the way the Vectrex format moves, it works up the screen rather than down. So I thought, well, we'll keep it the same, whatever. So I'm negating the Y position there just to make it work in the same format as the Vectrex did. Now the moves are basically the same. We're again loading in a Y and an X position. All we're doing here is we're then adding the red in X and Y position, and we are offsetting the current drawing cursor position in Y pos 24 and X pos 24 here. So that move will be applied to those, and that's all it takes. Now, of course, there's no line drawing here. The relative line draw occurs here. But that's almost all there is to it, to the draw packet format version of the code. Now, the VTX done we haven't seen. That's because it's shared within the draw C packet version, which, to be honest, is almost the same as well. Now, we need some more registers here, so this time we're using IX as our source data here. Now, firstly, what we're doing here is we are checking the top bit of IX plus 1, which is the X position, and this defines, if you remember, whether we're drawing a line or doing a movement. If I just go back here, we're basically checking this bit here in the second byte of the pair. So that's what we're checking there, and if it's a 0, we're doing a move, and if it's a 1, we're drawing a line. Now, we've got a different version of the Sine Extend command here because we've only got 7 bits this time, but basically we're doing the same thing here, reading the Y and X position, and we're drawing a relative line here, and alternatively, we're doing a move here, again, using 7 bits. Now, when we have finished, when we get our last command, which we are checking after the last draw, where is it? Just here we're checking to see if the bit 7 of the Y position was a 1, because if you remember, that will define the last command, which we're assuming is a line. If it's not a line, then you've kind of wasted some memory there. You know, there's no reason to do a move as your last command. And then what we're doing here is we're restoring the X and Y position here, and we're zeroing the low byte of the 24-bit triplet for the X and Y position, because that's the fractional movement, so we're recentering the position. Otherwise, you might get slight shifts depending on what you last drew. So that's the C packet version. So the major difference here is this Sine Extend command here, and what the Sine Extend command does is it's basically checking the top bit of C here, bit 7, and it's effectively filling B with whatever that top bit of C was. The 7-bit version is almost the same. All we're doing here is we are effectively using bit 6 and we're setting bit 7 accordingly and then doing the same thing. Now, Sine Extend BC does have a bit of a trick. You'll see it drops into this do scale command. Now, in some cases, we need to scale our objects, and so what this is doing is it's loading in a scale. A scale of 0 is normal size, a scale of 1 is double size, and a scale of -1 is half size. Very crude scaling, not proper scaling, but it's fast, and that's all I needed in this case. So here we're just shifting the bits of B and C according to the scale here, and this is a quick way of allowing us to scale things up or down. So that's how we're doing our packets and our C packets. Now, these are then used as a font driver. So basically, rather than use a raster font, which I thought would be quite boring and not really in keeping with this tutorial and this program, what I've used is a vector font, and the vector font is in C packet format. So that's a C packet letter A, and you can see all of these letters going on here, and then we've got some numbers here. So these will draw simple, it's very simple in some cases, vector characters, and you can see we've got only a limited character set here, A to Z in uppercase, and some symbols here. So if we go back to our vector code here, this is the code that handles that. We've got a classic print string routine, which we've done before. Basically, what we're doing here is we've got a print char routine which is compatible with the original print char routine in my other systems. My monitor, for example, can use this, and so we're backing up all of our registers so nothing is negatively affected here. And then what we are doing is we're just comparing to see what kind of character we've got. We're then loading in the address of the lookup table. Where is it? One of these lookup tables here, which contains a set of pointers to the packet data that we need to draw to the screen. We're subtracting the first character within the lookup table accordingly because we need an offset within that lookup table. We're then doubling the remaining value, which will now be the character number within that lookup table. There's 2 bytes per entry in that lookup table. We're then loading in an address from the lookup table here into IX, which is going to be the C packet we want to draw. We're then drawing it to the screen, and then we're offsetting the X position by 12, or whatever 12 would be depending on our current scale, to move the drawing position along 1 character here. Now that's how we're drawing characters to the screen, but of course we'll need some way of moving the drawing cursor, both for drawing characters and for drawing just packet data, and that's what our locate command does here. This will set the top 2 bytes of X and Y position, and it's zeroing the bottom byte here. I think there's actually some waste here, it's doing it twice. I think we could take that out, it will work fine. Should have cleared that up maybe. Anyway, that's what we've done here. Now, of course, we can see all of this in action on our screen here. This is not using the font. This is a packet, I believe. Parts of this are C packets, just depending on the amount of detail needed, because a C packet is only 7 bits of movement data and a packet is 8 bits. So sometimes for things like the tongue, which needs a nice smooth curve, maybe it's not appropriate, but for these walls, these are C packets. Now the text here is being scaled down. The normal size, I believe you would need to see the game over screen. If I can just remember how to play this game. No, I cannot. If we just quickly kill ourselves. There we go. So you can see here that this is being scaled to multiple sizes here. This is big, this is smaller, and if we go back to the title screen, this is the smallest. So we've got the ability to scale the font within certain limitations. As I say, maybe this is a little bit too small, but by using those powers, half, quarter, eighth kind of movements of scale, it's a lot easier to program and it's a lot faster. Anyway, that's what we're covering today. That's the line drawing routines and the vector routines. I had a lot of fun writing these. It gave me a certain twisted satisfaction to port Vectrex routines from the 6809, Vectrex formats rather, to the Z80. I enjoyed that, so that was amusing for me. As I say, the line drawing routines we looked at today aren't amazing, but I don't think they're too bad either, and hopefully they're relatively easy to understand. Anyway, if you've liked what you've seen today, please like and subscribe. As I always say, if you like the videos, YouTube recommends them to more people. And if you subscribe, I just might do that better line drawing algorithm. Otherwise, maybe I won't. Who knows? Anyway, I hope you've enjoyed this, and I hope it gives you some fun and entertainment for your own Z80 projects. You can, of course, download all my source code and do whatever the heck you want with it. Have a lot of fun. Thanks for watching today, and goodbye.